All right. Good evening. All right. It's okay. I will give a very simple one. My slides are very simple ones. I will give. This is a semi-public talk, so you don't need sophisticated knowledge in general relativity or to understand. But if you do have those knowledge, this will also will help. Okay. This is the outline of my talk. What are we made of? What is antimatter? What is the universe made of? Why do we need dark matter? And there are also open questions and alternative theories. What are we made of? This is actually what we need. Maybe turn off the first. Thank you. We all know we are largely water, but by mass, water are largely oxygen. Well, 65% of mass is oxygen, and second common one is carbon, and hydrogen, which is mostly in water. And we have also nitrogen in protein and others. Among these others, there are also some ones altogether less than 1%. We have boron, chromium, cobalt, copper, and etc. So that is all the necessary element to make a human being. So if you start from atom, that's the type of atom you should collect first to create a human being. Actually, these are very important information highlighted here. For example, the most heaviest one is iodine here. They are heavier than iron. This is a periodic table. I got it from Wikipedia. I circled all the elements made for us. And here we have a few small ones. Include zinc, heavier. I think that's it. Yeah. In Chinese, they have the same sound. Yeah, that's the thing. Anyway, zinc is heavier than iron. And you have, well, we didn't exhaust the periodic table. You can make much more complicated human being by using higher ones. But the information from here means we are all made from the stardust. Why is that? Because the stellar thermonuclear burning has an end point. What does that mean? Okay, we know how the sun is powered. Inside the sun, hydrogen, 4 hydrogen atom eventually fuse to a helium. Because the binding energy, well, for hydrogen there's no binding energy. From the deuterium, for example, to the helium, the binding energy is increased. So when you make a helium, you make them bonded tighter. Therefore, you release energy. That's how the sun can power us. And inside the sun, later on, when the hydrogen is being burned out like 20% now, and the helium may further fuse to higher ones, carbon and oxygen. Well, lithium is pretty tricky business. We'll come back to that later, and eventually it goes on. So every fusion gives you more and more energy, but the less and less, you can see, is the levels off. It's not like from hydrogen or deuterium to helium, right? Dramatic. Most of the stars is powered by this fusion reaction. But when you reach the point ion, it stopped. Because further fusion does not create energy, require energy. Because anything heavier than ion, the bonding is loosened per per element, per hydrogen, per nucleus, per proton or neutron. The binding is lighter, so you want something to fuse to lead, you actually need to pump in energy to create that one. I remember there are some of the elements are heavier than iron here. These guys cannot made by our sun. So therefore, where can they really came from? And it actually not only cannot be made by our sun, cannot be made by any thermal burning, any stuff, even cells. There only one process can violate this to create hydrogens. We know on Earth we saw uranium. That's why the atomic bomb came from. We have uranium. Where are those uranium came from? The only one process so far we know can be systematically produce very heavy ones, which is supernova. Supernova is very violent. It's also a burning sun, but that sun required to be much heavier. But when it's burning to about this stage, the burning stopped. Nothing can sustain the burning, the core will collapse because gravity is always there. The reason sun is not collapsed yet because this burning releases so much heat, so much energy, the heat suspended because all the particles moving so fast, you cannot really squeeze it by gravity. But when the moving so fast process, no fuel to fuel the process, and then gravitational collapse will cause this. And for such large object, the collapsing is more dramatic. The core part is collapsed, but the shell part actually be shattered away. Anyhow, this process is very violent and can create any atom you want. So therefore, our sun must be at least a second generation star. We are made of the dust of the previous supernova. Every one of us. Because without this element, you will die. Well, that's what we are made from. The question is what we are made of. Well, we are made of those elements, and elements are atoms. Atoms, for example, here, this is a real picture of atom, of a helium atom. This is roughly the size of this electron cloud. And you don't see the mini solar system ones, okay, because the electron you cannot really see it. It is a distribution. And the size of the atom is about 100,000 Fermi, which is a unit. So 10 to the minus 15 meter. Well, anyhow, it's a very small number, so that's the size of the atom. And that's where the nucleus is, which is the size of 1 Fermi. In this picture, in space, we are largely made of empty space. The heavy part at the center, because you can see the mass of proton and mass of neutron are much heavier than mass of electron, almost 2,000 times heavier. So from the mass perspective, electron mass in our body is negligible. We are largely protons and neutrons. So we are made of hadrons or nuclei. Well, as a physics student, you all know protons and neutrons are not fundamental particles. They are made of quarks. Quarks, for example, proton has 2 up quark, 1 down quark, and neutron 1 up quark, 2 down quark. And the color is the color charge they carry, make the whole proton colorless, and whole neutron white colorless, which means the whole thing does not carry a strong charge, which we don't fully understand yet, but that this model fits the data pretty well. Who have UUD and UDD for proton and neutron? You all heard of this, and they are fundamental particles. So this is the list of not all known fundamental particles. A couple of years ago, we discovered the very last one, Higgs. So we have the orange, purple ones are quarks, and these are called leptons. They are fundamental, and here we have a familiar guy, electron here. Proton and neutron are not fundamental enough to make this table. They are making another layer of periodic table. So this is our modern periodic table from the fundamental particles. And these red ones are called gauge bosons. They carry forces. And there's only one scalar Higgs boson, which from the news you probably heard, and also the Nobel Prize. They gave us mass. But they really gave us mass. Okay, proton have three parts, up, down. And here I label the mass of each fundamental particles. They're changed very dramatically from the very light one. We don't know whether it's massless, but we know it cannot be heavier than that number, 2 electron volts. If you use astrophysics data, it's even lower number than that. And the heavy ones on this, I think the champion is top part, which is 173 G 10 to the 9. So that's a 10 to the 11. That's an 11 order of magnitude different. We don't understand this. That's that. But let's just look at the simple ones. The protons. Quark mass came from Higgs bosons. In the standard model, because of the interaction between the quark field and the Higgs particle, that gave us the quark mass. Okay, so that is across in our model, standard model. So the quark mass, the ones we have so different quark mass here, they came from interacting with this yellow band. Okay, now let's look at these numbers more carefully. Up quark mass from the previous slides is approximately 2.3 MeV. Divided by c squared if you don't use atomic unit. Down quark is slightly heavier, it's 4.8. With unlike top and bottom, top quark is heavier than bottom, but up is lighter than the down. You can add them up. For proton, 2U, 1D is 9.4, and proton is 938. And so that is just. Oh, actually, I did the slide is wrong. This is just 1%. I thought it's 10%. I overestimated. So it's 99% of the proton mass is not from the quark mass. Quark mass are due to the interaction with Higgs. So therefore, 99% of proton, if it's using neutron, then probably 98%, because neutron has 2 down quarks. Very heavy. So that means the most of our mass, the proton mass, is not from the quarks. Therefore, Higgs are not responsible to our mass. Okay, so whatever the media you heard when the Nobel Prize was issued a couple of years ago, saying Higgs gave us mass. No, Higgs didn't. Higgs only gave quarks mass. Quarks mass is a very small portion of our body.
So how do I say?
Okay, how you explain? Yes. That is how you explain it. Einstein can explain it to you. They are interactions. They are dynamics. Well, the popular notion for the mass is for the Einstein's famous equation is E equal to mc squared. But in Einstein's original paper, he didn't write E equal to mc squared. He rather write m equal to E over c squared. Of course, by mathematical point of view, there's no difference. Unless you are an engineer. You're an engineer in this room, right? So I can make it fun for during the World War II, in the United States, in the United Armies, there are handbooks for engineers. They are working with radar. So there's two major projects. One is, you already know, the Manhattan project, making atom bomb. There's another one just as important, is making radars. And when in the handbook, they have many fundamental laws for the engineer to use, to remember, to plug in. For example, Ohm's law. Ohm's law said resistance equal to voltage divided by current. And second Ohm's law, voltage equals to resistance multiplied by current. Third Ohm's law, current equal to voltage divided by resistance. So that's the first equation. So if you have a very strong interaction and quarks are very strongly interact with each other, we call that interaction strong interaction called reason. But it's stronger than electromagnetic, that's the reason. But it's really strong. So it's stronger than the electric or Coulomb repulsion. Even they have a charge, the same sign of charge, they still combine very heavily. And that is all the mass really came from. It's those interactions divided by c squared. That's give us. So that means we are largely made of matter. Not from quarks, from interaction. So if we have a model, we think about a model, the quarks are massless. All the quarks are really massless, not this massive, but really massless. We didn't lose much. We're still here. More than 95% of us still here. Now more than 95% of us, our mass are not from Higgs, are from nothing, from the dynamics. Okay, that is the first agenda. Second one, antimatter as matter. In the universe, actually, this is protons enough. You add a little bit of neutron because in the universe, the visible matters more than 75% are hydrogen. And hydrogen is only have one proton, no neutron. The remaining mostly 25% are helium, which have half proton, half neutron. So neutron is not that important compared to the proton. And all those fancy fundamental particles, all those guys are not important at all in the universe. There's another question, it's called Ravi's question. Who ordered? Why do we need them? We don't know. But we have some clues, but not definite answer. More than that, actually, that table, the new periodic table, is not really complete. There are antiparticles for most of the particles. Only very few does not have antiparticle, like the photon. Photon's antiparticle is himself. It does not have antiparticle. Higgs does not have antiparticle, and Z0 does not have antiparticle. W plus or minus are antiparticle to each other. Every other particles has an antiparticle. So the new periodic table should be not 17 particles I showed you earlier. It should be 61. For example, electrons, and there is a positron. Electron, neutrino, anti-electron, neutrino, muon, anti-muon, etc. For the quarks, we have arc quark, but arc quark has 3 different colors. So you may consider color as a fancy electric charge. We all know charge, what is electric charge is. We don't have magnetic charge. But in fancy theory, there is a fancier charge, more interesting one. And physicists are so like to confuse the layman. We didn't invent a new word. It should call strong charge or whatever other charge. We call them color. That has nothing to do with color. That's a name. Just like each name of quark, we also call them flavor. There is a flavor dynamics. It has nothing to do with sweet and sour. So these colors is just a way to label them. there are 3 colors, right? Well, we use 3 primes, so since there are 3 colors, that's the reason we call them color in the first place. We call the 6 type of flavors because flavors, at the time when they named it, they thought there were only 4 parts. Actually, it's arguable we have 5 flavors. GSM, MSG. MSG is probably a new flavor. Spicy. The spicy peppers is not a flavor. That's just paint. That's literally is paint. That's not a new flavor. So now we have actually 6 flavors. We don't bother to name them sweet. Sorry. So that's the color in quarks. And the anti-quark not only have anti-charge, negative charge, also anti-color. So for the red, this is anti-red. It is really called anti-red. But we know what is anti-red is. Whatever these 2 colors meet together give you white. So this anti-red is roughly what is it called? Sand. That is anti-green is more purplish, anti-blue is yellowish. And for gluons, we have 8 gluons. They all massless, no mass, doesn't carry any charge, but they carry the color charge. And for them to carry color charge, because that's the bonding between the quarks. Just like when you have 2 charges, they repel each other because they interchange photons. The modern view of interaction. And similarly, why the quarks bond together, they interchange gluons. And for this, since they are fancier, so we have more than 1 colorful photons here. We actually have 8. This one's also the color here is not arbitrary. They actually colors, and 4 of them are the antiparticle of another 4. And you can see if I think each color will be, well, the mathematics is slightly evolved, but that's the color meaning here is similar from here. So you need to make 8 different colors. Well, gluons to carry the energy. Photon, on the other hand, another reason for photon to be particularly simple, photon itself is chargeless. Although he responds for electromagnetic interaction, but he himself doesn't evolve, doesn't get repulsive or attractive by a charge. But gluons, you can see this theory are complicated, but the gluons themselves are colorful. All the colors undergo strong interaction. So that is really the correct fundamental, correct modern periodic table we have. We have 61 particles. However, we do understand why we are all made of matter, not antimatter. Our sun made of matter, our moon made of matter, and it seems to be our entire galaxy are made of matter, and all our nearby galaxies probably made of matter as well. We don't understand why. This fundamental question is called baryon asymmetry problem. The imbalance in baryonic matter, baryonic here is just a fancy word of saying the hydrogen or protons, the heavier ones. And antibaryonic matter in the observed universe, we don't know why they are not balanced out. The reason is our model is completely symmetric under the combination of CPT, here C, is for charge conjugation, which is if you change particle to antiparticle, P is change space, T is reverse time. If you do all 3, of course, particle will become antiparticle, travel in the backward time and in the mirror space. Our theory is completely symmetric. So therefore, if the theory is symmetric, it would be obvious to think the solution of the theory, which is this word, should be symmetric. Not symmetric under particular one, which Yang Qinghai and Li Jingdao already won the Nobel Prize for disprove that. But the combination are still a good symmetry of this model. We don't see any violation from this. So if there's no violation, then we should be symmetric between baron and antibaron, or between matter and antimatter, and we don't know why. There are possible solutions. CPT altogether are conserved, but any one or two of them are not conserved. In particularly, the CP, combination of CP may be violated. There are two types of CP violation, which is one is called strong CP violation. That means the CP violation in the strong interaction. The interaction will involve quarks and gluons. Our model allows strong CP violation. The standard model has a free parameter. If that parameter not equal to 0, we would have strong CP violation. But however, all the current data shows that parameter is really 0. But we don't have a fundamental principle saying it should be 0. We just measure it, and it's very much like 0. It's often in the history of physics, if something really, really want to be 0, it should be identical equal to 0. You may have a better theory to describe it, the result is really 0, not approximately 0. We almost never have something approximately 0, either 0 or not 0. Weak CP violation being detected and also widely used, and also several Nobel Prizes being issued. But the problem with these two guys is for strong CP violation, if it's really a violation, it will be too strong to explain the matter-antimatter asymmetry. So that we would have much more matter than we expected. But if it's totally, for some reason we don't understand, totally be turned off, and we rely on weak CPI violation, which is the CPI violation in quick interaction, that would be too weak. I use weak in different meanings. Weak here, the weak interaction, but it's too small of an effect to explain the observation data. So this is still a fundamental problem we don't know how to solve. Of course, there is another theory. The reason we see a lot of matter around us, we solve this symmetry, we assume all the observed universe are made of matter just like us. There may be the neighbor galaxies are made of antimatter. And if the half of the galaxy is made of matter, half the galaxy is made of antimatter, we are fine. Or maybe small but imbalance can be explained by the weak violation, we are also fine. But the problem with this is, what about the boundary between the matter region and antimatter region? In the boundary, matter and antimatter will meet each other, and they don't like each other, they kill off each other. When they meet, they immediately become purely energy, photons, radiation. So we should see these boundaries shining in the universe. We haven't seen any structure like that. You may say, well, maybe the boundary is very, very dilute. The chances are very slim. That's possible, but it seems not really fitting the calculation does not really fit in the observation. Unless you have some other mechanism to avoid they cross each other, really make a purely vector. That's possible, but we don't understand that yet. So this is one open question. Okay, I have matter covered, antimatter covered with open question, and the third question: what is the universe? This is the I'm going to use the standard cosmology model called lambda CDM. Lambda stands for dark energy, lambda. DM stands for dark matter, DM. C stands for cold. Only one particular dark matter is appear in this model, which is cold dark matter. So they don't really radiate very much. They are not hot, not like our sun. So that's why you can't see it, because they are very cool. And that's the majority of the universe, 4.9%. It's not really clearly. 4.9% are regular matters like our sun or nebulas or us. Yeah, from this point of view, we are not really significant in the universe. 0.1% of neutrinos and 0.01% of photons. In this matter part, and matter and dark matter, if you put these two together, actually, all this together without the dark energy, all this together, the majority dominated by dark matter. And that is regular matter we're familiar with, and these are possible neutrinos. We are not sure. They depend on the neutrino mass. We know neutrino probably not massless, that's last year's Nobel Prize, but we don't know what's really the neutrino mass. So there's ambiguity there. So why do we need dark matter? This is artistic illustration of dark matters. If you have a galaxy, dark matters distribute much wider than matters. Now, like matters are like to constrain on a disk. Almost all the young enough galaxies are in the disk-shaped spiral. Okay. This is due to gravity, gravitational effect. But dark matter is more distribution is more like spherical, symmetrical. And dark matter only involved in gravitational interaction and does not have any electromagnetic. That's why we couldn't see it. It doesn't participate, doesn't shine light out. There may be also evidence show the dark matter seems to be clumped together, but it's not very dense. We never came across collide with the dark matter. Okay, here are a few examples. I will show one by one why do we use dark matter in the standard cosmology model. The most popular reason is to use dark matter to explain galaxy rotational curve. What's a galaxy rotational curve? If we have a galaxy, there are many stars here, we can measure the velocity of these stars. And we can also add up all the masses inside. Even though it's an irregular shape, but we know gravity pretty well. And at this scale, the gravity is Newtonian gravity. Inverse square law is good enough. Because the gravitational force is weak, they're very long distance. We're not near any black holes. Only when you're near black holes or near the sun, you need to worry about the general relativity. This is just Newtonian gravity, inverse square law. So even a high school student can calculate what the speed inverse square law will give us. This should be the dashed line. It should be. So when it's really further away, because the force is much weaker, the speed is slower. The speed of Jupiter is slower than the speed of the Earth when they circle around the sun. By the same reason, the speed of a distant star will be slower than the nearest star when they're spinning around the whole galaxy, or largely accounted for the central black hole. But here is the observation. It doesn't decay at all. From the visible light, like a Hubble telescope can see, those are from the hydrogen radiation. Those probably more radio wavelength. 21 centimeters. But these are the data, and that is the expectation. So therefore, there one simple and intuitive explanation is you didn't measure the mass carefully. Because there is lots of other mass here. If we have heavier mass, then of course the speed will be higher even at the same distance. So therefore, to fit this curve, you need lots of mass you haven't seen, this dark matter, to fit this curve. For each galaxy, you need a distribution of dark matters to fit the curve. And of course, this curve can fit pretty well. And this is the most intuitive explanation. When you see a discrepancy, either your model is wrong, or if you believe your model, there's something you didn't see. And that is the matter we didn't see. If that's the only reason the dark matter model is not that appealing, because this can easily, later on I can show you alternative theory better than dark matter, easily overdrawn. So we could have a better theory. But there are more. For example, gravitational lensing. So if you have a galaxy cluster much heavier, and suppose behind the cluster there is a galaxy, then we know Einstein's gravity light will be bounded when they passing through gravitational field. So therefore, for this galaxy, we can see one image is here, another image is here. So using these images, how much angle they came from, we can estimate how much matter, how much gravity should be inside to make such a banding. And in this calculation, once again we found the light banded much more than the stars we really observe. So therefore, there's something else really want to band the light, and it's actually from both here and here, the dark matter to visible matter ratio is about 5 or 6 to 1. So we have more dark matters than the regular matters to explain this data and those data. So therefore, we have one hypothesis. We exist dark matter. We already explained two independent data. These are motion of, if you like, time-like particles. And these are motion of light-like particles. They're different. There are more, actually, more appealing evidence for dark matter. This is one of the things probably most strongly. This is called large-scale structure. Each point in this figure represents one galaxy. And that is, of course, is a huge supercluster. And if you zoom in, that is a cluster. That is zooming from here. Those are zooming from here. So in a very, very large scale, this is 1,000 mega parsec. Parsec is a unit, astronomical unit is when the astronomical unit looks like 1 second in the angle. So it's a bit more than a light year, 3 point something light years. It's a unit longer than light year. It is often used because it is in the calculation. So that's a very, very large distance. We have this web shape of structure. This is a simulation. If we compare this simulation, in this simulation they use dark energy and dark matter to simulate. And here is observation. Observation, look at the near region, we can see this very similar structure. They are actually not only qualitatively similar, they are quantitatively similar. You can measure what is the average distance between galaxies compared to this figure and this one, this simulation, and they do match each other using the current observed data as the input to simulate. The reason we don't have this overall uniform structure is because light travels at a finite distance. when we look further away or larger region, we actually looking at the history. The long time ago. It's now the current state. The simulation is simulated at a time slide like now, what the universe would be, but we are living now at here, and now nearby galaxy, which they live 100,000 years ago before the mammoths still exist, and some other galaxies living with the dinosaurs still running on the world. So we are looking not only further distance but also in history. So therefore, in the very long distance, you have different structure because that's really a universe. So anyhow, that is one example. Another evidence for dark matter is collecting galaxies. If we have a galaxy, they have a dark matter halo around it. If we have another galaxy, a dark matter halo around it. And there are chances the two galaxies may run into each other. When they run into each other, dark matter, by its name, the reason it's dark is it doesn't participate in any interaction except gravity. So therefore, they don't carry each other. They're like transparent, just passing by. But the matters, they do participate in interaction. Mostly importantly in this context is electromagnetic. That's why when you matter clash, you can see they're heating up temperature. If a large matter clash, you can see brighter light come out because of those electromagnetic interaction. So therefore, when the two galaxies collide, matters and antimatters may no longer hold together. They may polarize in a sense. Because not antimatter, sorry, dark matter. The dark matter may just going through like nothing happened. And the matter, they interact. And that is what is expected if we have dark matter. And here is evidence. There are two colors. This pink color are the mass, mostly in this case is a gas, mapped by X-rays. How much X-ray emitted. So during this collision, there are X-rays emission. So we can see there are lots of X-ray here, lots of X-ray here. Those are mostly what is the regular matter. Where is the regular matter? The blue ones are the map to the total mass by lensing, by look at behind the stars. The light is slightly bending. So that will give you the total mass, matter plus dark matter. And you can see the center mass are not the same. Because dark matter dominant, 5 to 6 to 1 ratio. So therefore dark matter really, as expected, passing by, and the matters, they are lagging behind. So that is another evidence. But of course, you may challenge this evidence. It's kind of weak. How you really model this, since we don't know what is dark matter. The last evidence, that's actually the most appealing one, is this. To explain the last evidence, let me tell you a little bit history about our universe. The standard model also predicts we are actually, our universe is born from a Big Bang. Long time ago, 13.8 billion years ago, we have some funny things happen at somewhere, actually here. Universe is this size. And after the Big Bang, there's some very strong interaction we don't really understand, but at one stage, which is 380,000 years after the Big Bang, and the things is so far apart, the photons or the heat, the energy, the heat stop interacting with each other. Before that, they're so dense, they're so close to each other, they exchange energies. After this year, these are so far apart, the last interaction between photons are stopped. After that, photons just keep going together with the universe expanding, and eventually some of them will reach us. Because they reach us at much later time, the size of the universe is much bigger, so they're cooler. And the temperature now is 2.7 degrees Kelvin. But that time, of course, is much hotter. But that is the time they stop interact with each other. So our current observation of so-called cosmic microwave background radiation is a snapshot what happened then at that moment. Of course, they have trace of what happened before that, but they don't care what happened after. Later on, the first star only shined 200 million years after the Big Bang, and now we have this picture. So therefore, if we measure the cosmic microwave background radiation, we will know the information about that time after the Big Bang. And the radiation, when we observe it, we found it's largely homogeneous. Almost, you look at every direction, they have same temperature. But if you measure it very, very carefully, that temperature is slightly different from one another. So it's 2.731, 2.730, 2.732, things like that. It's a 1,000 order of that much of difference. So we can map those difference in this figure, which is the cooler one. The blue one is colder than the average, and the orange one, red one is hotter than average. But these are exaggerated. The cooler one is maybe 2.730, and this is 2.732. They're still largely in the same, very homogeneous. So therefore, when we have this, we can, this is a spatial distribution. We can do Fourier transform. So, to further explain that, I will do Fourier transform in a moment. During this expansion of the universe, actually the current model, the standard model, how much time do I have?
It's like, you actually overrun already. It's okay, you can continue.
Okay. Now starting. Okay, this slide is very interesting, so I will cover it. I will try to speed up. This is our understanding, this standard cosmology model. And you can see, for those second year or third year later students, you will see something screwy here. This is how matter dilute in the universe. When the universe expanded, matter just become more and more dilute. So therefore, it will go down as the size Q. The density going down by size Q. However, photon light does not only dilute, but also the wavelength is stretched. So therefore, the photon energy density goes down by length to the fourth power. And if we have that energy, and they don't go down. They don't go down at all. Because they are space themselves. So what part is screwy here is, what is the particle wave duality? This is a very classical view, and it's fit data fantastically well. No particle wave duality. So you cannot think in this picture, electrons are actually electron waves. If it's waves, when the space is expanding, the wavelength will expand. We didn't see that. The electron doesn't expand, only getting diluted further apart from each other. Only photon getting expanded. I don't fully understand this. I asked several physicists about this. All those pretend to be understanding. One way I can say is one mechanics to explain this is maybe to over simplify. Total energy not control. Oh, you mean this one?
Total energy density, yeah. Why is it?
Oh, because it is space, so it doesn't change. So it is not really energy. Well, energy is, well, I will come back to that. Energy is a misinterpreted name. It is just a space itself.
Something like fuel energy.
No, it's not really energy. It's something we require have that property. Let's put this way.
Okay.
That will fit the data. So therefore, if now I show you this figure earlier, we have 68% of dark energy, and long time ago, 380 years ago, there was no dark energy, because that time the size is much smaller, and energy density doesn't shrink. But if you go back, everybody increase. Matter and photon all increase, but the energy, dark energy itself doesn't increase. So therefore, at that time dark energy is negligible. We have dark matter at different ratios, and neutrino photons also quite important then. So therefore, using this, we can simulate data. What cosmic background? This is last time cosmic microwave background interact with each other. So we will using this, we can simulate data, and this is the fitting, the data. The dot is observation, and the red one is the fitting. Not fitting. This is the model calculation. You can see this neat, fantastic work. Here I'm using a multiple moment, which illustrates this scheme. So this, to get this peak, we need a specific ratio of matter, specific amount of neutrino, photons, and all this. So therefore, this is the strongest evidence dark matter really should be there, at least 63%. Then to give you this. All right. Dark energy, the lambda is actually a rebranding from cosmological constant. So if you add a cosmological constant in the Einstein field equation, and when we have dark matter, some physicists, I don't know who, did a really lousy job. We call it dark energy, which is not really energy at all. It is a constant of the universe. The total amount of matter, and dark energy determine the curvature of the universe. If our universe have lots of stuff, it will be closed. If less stuff, it will be open like that. And if it's just red stuff, our universe will appear to be flat. And that is the observation. There are three observations here. Cosmic microwave background, that's observation. The horizontal axis is the total matter plus dark matter. Vertical is dark energy. And this is supernova observation, and the green one is called baryonic acoustic oscillation, which is those peaks we have seen earlier, or in the large scale structures we have seen earlier. You can see the three observations really fit each other, and the common region really give us flat. How dark energy changes in time, I will determine the future of the universe. If dark energy is constant, will going on like this. The universe will become more and more dilute. We'll see fewer and fewer stars. Eventually, we'll only see our own clusters, no other stars. The light cannot reach us because the expansion is very fast, can be faster than speed light. So therefore, if the faster than speed light, we cannot see. Now we already cannot see many stars outside our horizon because they move too fast away from us. But if dark energy decreases somehow, and we may have a warm welcome big crunch at the end. A big rib is even cooler. Here are the open questions. We don't know why the baryon asymmetry. There are a few problems can be explained. For example, the flatness problem. We seems to be flat, but we don't have understanding on that. But there's one model can count on that. It's called cosmic inflation. So if at the beginning of the Big Bang, something dramatic happened, the expansion is exponentially fast. Okay? Like in 10 to the minus 14 seconds, you expand the whole universe by a huge factor. If those things allowed, then it can explain the thermodynamics problem. As a result of that inflation, we would have flat universe. That is one hypothesis. We haven't discussed that. And horizon problem is similar. That is the fluctuation of cosmic microwave background radiation. It seems in the very far region they still correlated to each other, which they shouldn't be because they never have a chance to travel at the speed of light. So it's too homogeneous, and that is also can be explained by inflation. We have also a problem is called lithium-7 problem. The lithium-7 seems to be smaller than the observer. For outscape is too technical. And also recent discovery is maybe our standard candle in the astronomy, which is type 1a supernova, may not be that standard. We consider all the type 1a supernova has exactly, or not exactly the same shape of size and brightness. So if we see the color, we know exactly how bright it should be. But if there are two types, they have same color, different brightness, then it's no longer good standard candle. So we don't know, we cannot really observe the brightness and reduce the distance. So that is one question. Related to that, Hubble constant also have a little bit of problem. That's a different observation. The Hubble constant in the large is quite consistent, but you can see their error bars not overlap. It could be a fundamental problem, or it could be just those guys overestimate their errors, underestimate their errors. They draw too small of error bars. It's often the case. The biggest open question is, what is dark matter? We seem to really need it, but what is it? If we can learn anything from the history, if you really want something and you search and search for a long time, you didn't get it. It could be you didn't search hard enough. For example, atoms. Scientifically predicted in the 80s, and 100 years later, this felt very short. There are other ones in the biology predicted by Harvey in 1628 and found it several decades later. They are also negative dark matter problems. For a while, we thought ether must be there because that's how light can propagate. And we look at it eventually. Nope, it's not there. There is a better theory. Don't need it. Vulcan is another one. Is accounting for the perihelion precision of Mercury. We observe the Mercury precise oddly compared to Newtonian gravity. Now we understand because it's Einstein. But before we propose, there is an inner planet called, we even give a name for Vulcan. We are very good to naming things we don't know at all. Volcano has the same root. It's work. There are alternative theories. One is called MOND, Modified Newtonian Dynamics. They fit the rotational curve very well, even better than the mass model. But it's hard to explain the large-scale structure and hard to explain the cosmology. Another model is called conformal gravity. They are also very appealing. They can fit the rotational curve with one parameter for more than 100 galaxies. The dark matter model, for each galaxy, you have a model of how much dark matter you need. So if you have 100 galaxies, you need 100 parameters there. You have 100 parameters. But this model only needs one parameter to fit all of them. Very it's also possible, this model also possible to have quantized gravity. Quantum gravity of this model is not safe, not like Einstein gravity. These are the fitting of some of the galaxies. Actually, they are more than 100. More than that, it also predicts the rotational curve eventually will going down like this. The dark matter one eventually will going down like that, because when you really be far away, you including all the dark matter, but then fixed mass, you have inverse square law and that will dominate. So it will be very different tape. But we don't know yet. These are the observation. Observation cannot tell what kind of tail will really come. There also not so good, not so appealing feature is when people calculate the gravitational lensing effect, the second evidence. So the first evidence both pretty good. Second evidence not so good. And the gravitational lensing for this model, you will have less lensing than the GR one. You need more because we observe more. Observe the more, we need dark matter to account the extra bending. Really? Actually, quite recently, Yang Qinghai and I did a calculation. We found no, people did calculations wrongly. In some small region, the gravitational lensing, this is Einstein's lensing, that is the new model's lensing, it can be higher. So those previous calculations, they are faulty. Well, we don't know how to calculate other effects. Yes, we are working on this. Okay. Sorry for overrun. That's all for today.
Thank you for staying. Guidance outside, please help yourself. And many of you have any questions?
Yes, question I will stay.
Thank you.